Okay. Today we're going to keep looking at the circular motion and gravitation topic, and we're going to look at the gravitation part of that topic. This might be a little bit of a long one, but I think I'm going to try and squeeze it into one video. Let's get into it. So let's start by looking at this top section up here about fields and gravitational fields. I did try and squeeze too much into this slide, so I've had to split it up over 3 or 4 slides in the end. And first, let's just take a little bit of a historical journey back to, the 1600s and the 1700s, when the people like Isaac Newton were coming up with this theory of gravity and all that sort of thing. And at that time, the concept that two objects that were not in contact with each other could exert a force on each other didn't fit comfortably with the people of the time. Radio communication, mobile phones, radio, television, all that stuff was a long time away from being invented. Um, the 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 conventional wisdom of the time, if you wanted to exert a force on something, you had to be in contact with it. Now that we have all this sort of communication that happens through the ether of space, I think we're probably more comfortable with that. So what scientists did at the time to come up with to come up with explanations for these observations is probably almost what we'd consider now like a kid's cartoon computer game type analogy, and that was they came up with the concept of force fields. So, this force at a distance model, so the fact that objects weren't in contact with each other exerting a force, just didn't seem right. So basically, what they said is objects were surrounded by this gravitational field. Almost think of like the force field that you get to protect yourself in a computer game for a while. And it wasn't that two objects not in contact with each other were exerting forces on each other or interacting. It was that one object was interacting with the force field that surrounded that second object. And in the terms of gravity, we look at this with electric fields in the next topic. In terms of gravity, the gravitational field strength was defined as the force per unit mass. So if you put a mass into the force field of some large object like the planet Earth, how much force would it experience for each kilogram of its mass? And we defined that as the gravitational field strength G, and it was defined as a force per unit mass, so force divided by mass. Now, we already know from Newton's second law that acceleration equals force over the mass, so gravitational field strength is exactly the same as acceleration. So when we talk about the acceleration due to gravity, which is 9.8 meters per second, if you drop an object, it'll accelerate 9.8 meters per second every second. So after 1 second, it does 9.8 meters per second. After 2, it's 19.6, and so on. That was defined as the gravitational field strength, which, as I said, is at what we know as the acceleration due to gravity. Let's continue the story. So, Isaac Newton was the person that came up with basically the theory to explain what gravity was and to basically to quantify it, to put it into numbers, if that makes sense. So Newton's law of universal gravitation. So remember, we've had Newton's first, second, and third law. This is Newton's other law, Newton's law of universal gravitation. Some people think this should sort of be zero law. It should have been the first law. Is every particle in the universe attracts Every particle in the universe attracts every other particle with a force that is directly proportional to the product of the two masses and inversely proportional to the square of the distance between their centres. It acts along the line joining the centre of masses. I've underlined that bit because when we talk about orbits of satellites later on, this is going to be a very important point to use in our explanations. And it's not something it is part of Newton's law of universal gravitation, but I know it's not mentioned, for example, in the summary here, and sometimes it's sort of skipped over a little bit in some books. It might just say between their centres, but not be explicit that the force acts along the line joining the centre of the masses. So, it's easy to think of this one as a formula. The force is equal to the product of the two masses, m1 and m2, and inversely proportional, so divided by the square of the distance between them. So r is what we use for the distance between them, because generally these things are moving in circular orbits, and that is indicated by the radius of the circle. G here is, if you like, the constant of proportionality in this equation. If we think about a typical sort of y equals mx type line, if you draw a graph of f versus m1 times m2 divided by r squared, you would find that the slope of that graph there would be g, the gravitational constant, which is 6.67 times 10 to the minus 11. It's a very, very, very small number. And what that small number indicates is that gravity is actually a very, very weak force. As we go on and look at the electrostatic force later on in the year, I think that comparison will become more relevant. So this formula here, oops, didn't mean to do that. This formula here allows us to work out the force any two objects exert on each other due to their mass. And we know if we're standing next to someone in a room, we don't feel this strong attraction to them that just pulls us together. On the scale of the masses of humans, if you put in your mass and your best mate's mass, and you're standing a metre apart, you are going to get a tiny, tiny, tiny little force because of this really, really small constant. It really only becomes significant where you start to deal with things the size of planets. Okay, let's continue this story and look at a few more of these things I have on the left-hand side. So in this slide, we're really just focusing on this point here, explain that the gravitational forces are consistent with Newton's third law. Newton's law of universal gravitation is consistent with Newton's third law as the force object A exerts on object B is equal in magnitude and opposite in direction to the force B exerts on A. Now, if that seems a bit wishy-washy, not real clear, a bit confusing, think of a specific example. The force the Earth exerts on the Moon is equal in magnitude, so equal in size, and opposite in direction to the force the Moon exerts on Earth. So if we think of this diagrammatically, we've got the Earth, we've got the Moon. The Earth, due to gravity, is pulling the Moon towards it. We indicate that with this blue vector here. The Moon is also exerting an exact equal force in the opposite direction. So those two forces are equal in size or magnitude and opposite in direction. Finally, for this bit, we just want to look at this bit here. Explain the acceleration of the projectile is always downward and independent of mass, and we'll sort of do that probably second. And finally, we want to think about this part here, which is use Newton's universal law of gravitation and Newton's second law of motion to calculate the value of acceleration due to gravity g on a planet or moon. And we are going to use here the example of Earth, and we're going to basically show that the acceleration due to gravity, or the gravitational field strength, as I talked about earlier, is 9.80 meters per second at the surface of the Earth. So we know, let's think about this. We have the Earth here and some object M. Big M, little e is the mass of the Earth, which I've given here. And this object is basically a distance r from the centre of the Earth. So you can see, you can think of it going in circular orbit. That's why we'd use the radius. So the force this object experiences is equal to mass times acceleration. And that force is coming from gravity, and that is given by G, the gravitational constant, times the mass of the object times the mass of the Earth. That's the product of the masses, divided by the radius squared. So if we take those two relationships, we get basically that MA is equal to G, I will keep it colour coordinated, even though it makes it a bit longer to write. Divided by R squared. Now we can immediately see in that formula that we've got mass on both sides, so that cancels out, so that we get that the acceleration, and maybe I will not worry about keeping going with the colours now, the acceleration is equal to G times M of the Earth divided by R squared. And in this case, we are interested on an object at the surface of the Earth. So the gravitational constant is 6.67 times 10 to the minus 11 times by the mass of the Earth, which is 5.97 times 10 to the 24 kilograms, divided by the radius of the Earth squared. 6.38 times 10 to the 6 squared. And if you put that all into your calculator, you'll get an answer of 9.80 meters per second. So we can do that calculation for basically any planet or star if we know the mass, and we can work out what will be the acceleration at its surface if we know the radius, so how far is the surface from the centre of the mass. The other thing I just wanted to highlight here, which relates to this point up here, is this acceleration is proportional to the mass of, in this case, the Earth, or the mass of the sun or planet, star or planet, or moon, and the radius. It does not depend on the mass of the object that's falling. And in practice, we know this from the classic experiment done by, I think, Galileo, where he dropped the marble and the cannonball off the Leaning Tower of Pisa, and we see that they fell at the same rate. And we looked at that in projectile motion. All objects will fall at the same rate if we ignore the effects of air resistance. So that is, if you like, consistent with this relationship here, because the acceleration does not depend on the mass of the object that's falling. It only depends on the mass of the planet or moon or star that it is being attracted to. So the next thing that we need to be able to do is explain why the centres of the circular orbits of Earth satellites must coincide with the centre of the Earth. And this goes back to that little bit I underlined in yellow before. The force causing centripetal acceleration, which is gravity, acts along a line joining the centre of masses. So if we look at this orbit here, going around, its centre of that orbit coincides with the centre of the Earth. So that's fine, that's what we call a possible orbit, because gravity would act along a line joining those two centres, so that one would work. However, if we wanted to have a satellite that just sort of spun around the top or the bottom of the Earth, like this, the centre of the orbit would be, say, about where that red dot is, not at the centre of the Earth. So gravity would not be able to provide the force for that orbit because it doesn't coincide with the centre of the Earth. Again here, this one coincides with the centre of the Earth, so that's perfectly okay, whereas this orbit out here doesn't coincide with the centre of the Earth. So that Earth is not possible. So maybe, that one gets a tick, that one gets a tick. They're both possible, not possible, not possible, because the centre of the orbit doesn't coincide with the centre of the force, and that therefore gravity can't provide the force for that centripetal acceleration as it acts along a line joining the centres. Next, we need to derive the formula to work out the velocity of a satellite that is orbiting either the Earth or some other planet. So, what we know is that, and this is important when we do a derivation, that we justify where this comes from. We know that the force, the force causing centripetal acceleration is gravity. So the force causing centripetal acceleration is gravity. Now we know that this force causing centripetal acceleration, well, from Newton's second law, is equal to, just get my right pen back, is equal to mass times acceleration. But we know for circular motion that acceleration is equal to v squared on r. So we'll substitute that in there. And the gravitational force is equal to Gm, capital M indicating like the mass of the Earth or the mass of the planet, some other planet, divided by r squared. Then we substitute in that, so we get mv squared on r is equal to Gmm on r squared. Now, we can see we've got an m on both sides, so they cancel. And we want to get rid of the r on the bottom here to get v. Hang on a sec. Oops. Hang on. I think that's right. Want to get rid of the r, so I'm going to times both sides by r. And that cancels. And that r here cancels out with one of the r times r's there. So I think you guys are all pretty strong on algebra. That's why you're doing year 12 physics. So that simplifies to v squared equals Gm on r. Or if we want to get v on its own, we've basically got to take the square root of both sides, which leaves us Gm on r. Put my working in there, doing the same thing to both sides. So, first thing I've done there is I have derived this formula. The other thing that I've done is I've shown that, explain that the speed and hence the period of a satellite moving in circular orbit depends only on the radius of the orbit and the mass of the central body about which the satellite is orbiting and not the mass of the satellite. So the velocity for this orbiting satellite depends only on the mass of the central object, m, and the radius, and obviously the gravitational constant. So, yeah, the mass of the actual object isn't in this formula, so it has no effect. The velocity is not dependent on the mass because there is no relationship between the two. Okay. So now we're going to muddy the waters a little bit of circular motion and talk about Kepler's laws, which relates to elliptical orbits or elliptical motion. But by the end of this slide, we'll come back to more of the simple circular case. So firstly, Kepler has two laws of planetary motion. His first law says all planets move in elliptical orbits with the sun as one focus. Circular orbits are special ellipses where both foci are at the same point. Sorry, I'll come back to that. I actually wrote that again later. I didn't realise I typed that. So what is an ellipse? Well, if you wanted to draw an ellipse, you could put two pins along a line and then you could get a piece of string and you would tie it to both of those, a fixed length of string tied to both of those foci. And if you drag that string around, you'll get this oval-shaped object. And that is basically an ellipse. Um, I think, yeah, that's probably as much as that we need to know about ellipses. So all planets move with an elliptical orbit with the sun at one of these focus points. Now, the reality is for most of the orbits of planets, they are fairly close to circular. Some of the outer planets get sort of more squashed elliptical type shaped. But so the two foci, so foci is the plural of focus, the two foci are fairly close together. However, when we deal with things like comets, which we'll talk about shortly, we deal sometimes with much more elliptical objects where, say, if the sun was here, at some points it's very close to the sun, and at other points it's a long way away from the sun. So that's the first law. All planets move in elliptical orbits. The second law is the radius vector drawn by the sun to a planet sweeps equal areas in equal time. What does that mean? Well, if we've got this object here moving in an elliptical orbit, it will always, if we look at this area of this, it's not really a triangle, but it's sort of a triangle with an arc edge. I think we'd call it an arc. If we look at this area of this arc shape here, it will be equal to the area of this arc shape out the other side if the time frame is equal. So what we're saying here is the object here will move much, much faster when it's nearer the sun. So you can see in 6 months it covers a much greater distance than it does in 6 months when it's a long way away from the sun. However, if you work out the area of this arc shape here versus the area of this arc shape here, they will be equal. So hopefully that makes sense. Some people just look at that and it's really straightforward and simple. I know for some students, though, they do find this a little bit more confusing. The consequence of this is things move much faster when they are nearer the sun, particularly things like comets, which move in very elliptical orbits. I'll do a question on this shortly, and hopefully when we do a question and I show how you answer that question, it'll maybe make more sense of how you use these first two laws to describe and explain the motion of comets, planets, moons, and other satellites. Kepler's third law of planetary motion shows the period of any satellite depends upon the radius of the orbit, and it's given by this relationship here. However, we only need to worry about this relationship here for circular orbits, which is, as I said, a circle is a special ellipse where both foci are at the same point. So that we know that the velocity of the satellite we can give them by 2 pi r on t if we're only considering the circular orbits here. So 2 pi r is the circumference of a circle. T is the period, so the time for one complete revolution. So distance over time gives velocity. But we also know the velocity can be given by the square root of g m on r. We derived that earlier. So if we put those two things together, we get that 2 pi r on period is equal to the square root of gm on r. Now we want to get rid of that square root. That's a bit confusing. So the first thing we're going to do is square both sides, and we get 4 pi squared r squared over period squared is equal to gm on r. And then we want to get period here on its own. So if I times, basically, this will get a bit messy actually, times both sides by period squared, that cancels. So I want to get rid of the r here, so I'm going to times this side by r, and I'm going to times this side by r, which is going to make that r cubed in a sec. Oops, I didn't mean to do that. I just changed my pen by mistake. So that r and that r now cancel. Then we want to get rid of the gm here, so we're going to divide this side by gm. We're going to divide this side by gm. That cancels, that cancels. So that leaves us overall with a relationship that looks like 4 pi squared r cubed, because we've got r squared times r, divided by gm is equal to the period squared, which is the same as is over here that we've been asked to derive. So that is the derivation there that we need to know. So here's our typical Kepler's Law question. In 2018, a satellite transiting exoplanet survey satellite was launched. The satellite travelled in an elliptical orbit around Earth. The diagram shows an elliptical orbit. Using Kepler's second law of planetary motion, explain why a satellite in an elliptical orbit travels faster when it is closer to Earth. So if we go back to Kepler's law, so when we get asked to use Kepler's second law to explain something, a really good starting point is to basically state what the law is so that we clearly understand which law we're using, and then we basically just briefly describe how it applies to this situation. So in this case, Kepler's law basically states that the radius vector drawn from Earth to the satellite sweeps equal areas in equal time. So I've restated that law, and then just because it helps me, I don't know if it's going to help me get marks or not, I'm basically going to draw that on the diagram. So I'm going to say that is a time sometime there, and that is the area drawn, as opposed to some other time out here, same time. So those T and T, if you like, T equals T. It's just helping me think through this, and basically this area here will equal that area there. That's what that statement's telling us. So when we look at that, we can see that obviously the satellite travels much further in a set time interval when it's closer to Earth than it does when it's further away from Earth. Therefore, the velocity must be much greater when it's nearer the Earth, which is what it's asking us to say. So now I need to put that into words. Like I said, I don't know if the diagram's helping me getting marks, but it's definitely helped me think through the problem. So what would I write? I would say, due to Kepler's law, which I've just explained, and I could even maybe refer to my diagram, C diagram, or yeah, C diagram, that'll do. The satellite travels much further in a set, let's just say fixed, it doesn't matter, set, fixed, constant, in a fixed time interval interval, I don't know if that's right or not now, in a fixed time interval when closer to the Earth, and maybe I'll just label that on my diagram A, than when it is further away. Sorry, I'm going around a box on my screen here. Say in that interval there, B. And finally, probably just to get back to the question to say why it travels faster. If it's travelling much further in a fixed time interval, therefore it must be moving faster. So therefore, it must be moving faster. I have a little band across the bottom of my screen. That's why I have to sort of write around that. So that's how we can go about answering that question in a really clear way and making sure we get all 3 marks that are on offer. Hopefully that was helpful. Okay, I'm getting there. In this slide, firstly, we need to solve problems using these formulas here that we've already talked about. I'm going to do an example problem as the last part in the next slide, so we'll come back to that. And I'm sort of going to do a calculation here, which is an example of using these equations as well. Next, explain why a satellite in a geostationary orbit must have an orbit in the Earth's equatorial plane with a relatively large radius and in the same direction as the Earth's rotation. So firstly, what is a geostationary satellite? Well, a geostationary satellite orbit will stay above the same point on the Earth's surface at all times. So firstly, if it's going to stay above the same point on the Earth's surface as the Earth rotates, it must have a period of 24 hours. It must have the same period as the Earth. And secondly, it must sit above the equator. The reason it can't sit anywhere else, so it's got to basically rotate around the same axis as the Earth. So if that's the axis there, the Earth rotates around, the satellite has to rotate around the same axis if it wants to stay above the Earth. So for example, if it was trying to orbit around an axis, say like, I don't want blue there, sorry. If it was trying to orbit around an axis like that, still coincides with the centre of the Earth, but you can see it's not above the same place on the Earth. When it's down here, it's over the southern hemisphere. When it's up here, it's above the northern hemisphere. So it won't stay above the same place on the Earth. So can't do that. That won't work. It also has to go around the equator because we've already looked at impossible orbits. If it was, say, going to orbit around here, so say it was going to say above some point like that red point on the surface of the Earth as the Earth spun, well, that doesn't coincide with the centre of the Earth, so that won't work either. That one's out as well. So, can only orbit around the equator with the same period of the Earth. When you get those questions, sometimes it's hard to explain why it must orbit above the same place on the Earth, why it must orbit around the equator. But sometimes the best way to explain those is say, well, if it didn't do that, this is what would happen. And then it becomes obvious, well, if it didn't do that, it wouldn't work, so it must do that, rather than trying to argue the positive or the affirmative. Sometimes it's easier to demonstrate if the negative applied, then it wouldn't work. That's what I'm trying to say there. It's just a different way to explain points. So we've explained why it has to have an equatorial orbit with the same period as the Earth. Let's work out why must the radius be so big. So if the period is 24 hours, that's equal to 24 times 60 times 60 seconds, which is equal to 86,400 seconds. So if we take the period formula, t squared equals 4 pi squared times r cubed over gm, but we know the period, we want to know the radius, so we've got to rearrange that formula. So that becomes the radius cubed equals gmt squared over 4 pi squared. Hopefully you're comfortable with the algebra there. I've shown enough algebra already in this video. So that the radius is equal to the cube root of gmt squared over 4 pi squared. And we'll continue in this column here, and I'm going to need to write small to fit it all in. R will equal the cube root of 6.67 times 10 to the minus 11, that's G, times by 5.97 times 10 to the 24, which is the mass of the Earth, times by 86,400 squared, divided by, sorry for the small messy writing, 4 pi squared. Don't need to substitute in pi because I've got a pi button on our calculators. You're not going to lose marks for that. Hang on, just lost my pen somewhere there. So that is going to be equal to 4.22 times 10 to the 7 meters. Now we could subtract there the radius of the Earth if we want to just get an idea of the height. So I think that was 6.38 times 10 to the 6 meters. That's the radius of the Earth. So that gives us a height or an altitude above the surface of the Earth of, let me just work that out in the calculator, 3.58 times 10 to the 7 meters, or 35,800 kilometers if we want to get that into kilometers, which is maybe a little bit easier to imagine. So that's how we can show that it must have a really, what does it say here? Explain why a satellite in geostream must have a equatorial plane with a relatively large radius because of basically working out the mass there. And that's also an example of this solving problems with this sort of stuff. And it also leads into the next part, which is explain the difference between polar, geostationary and equatorial orbits, justify the use of each orbit for different applications. So geostationary, orbit around the equator, same period as the Earth. We've just talked about that. Polar orbit satellites, as they probably sound, but I will draw a quick diagram to show that. Here's our satellite, and a polar orbit satellite would basically go like that around the north-south pole. That's the equator there. So, what are some of geostationary satellites? They are used for communication, because basically if you have a satellite dish like your Foxtel or something like that, the dish needs to point to the same spot in the sky. So dish must point to same spot in sky. Seems a little bit unscientific, I know, but hopefully you know what I mean. They also allow you to observe a large portion of planet, because when you're that far out looking back you can always see, but the problem is, oops, just lost my pen there, but only on one side, because they're always above the same spot is the problem there. But one of the problems there is you only get fairly low resolution imaging due to the height. So we could probably go on to more, but they're the most important things we could probably say about a geostationary equatorial orbit satellite. Polar orbit satellites tend to be at much lower altitude, so you can get better resolution in your imagery. They also, because of their shorter radius and the velocity they move, they tend to basically have a period of about 2 hours. So what basically happens, as the Earth spins, they keep going around and round, and they can basically image at regular intervals the whole surface of the planet. So the period's about 2 hours. So I might put this in inverted commas. Earth, because the Earth spins every 24 hours. Earth spins underneath the satellite. So therefore it can image entire surface as the Earth's going around under it. It just keeps taking images of each new strip that's passing under it each time. So I think they're the most important things there. There's a few other fine ones, but I think if you remember those ones, you'll be well and truly on track. So one more slide to go, and I'll go through some of these example problems from a previous exam that we have here, where we talk about solved problems. Let's get on with this and get it over with. So, previous exam question. In 2013, 3 swarm satellites were launched to study the Earth's magnetic field. The satellites orbit the Earth in circular polar orbits, so north-south pole type orbits we're talking about. 2 of the satellites, Swarm A and Swarm C, orbit 462 kilometres above the Earth's surface. The third satellite, Swarm B, orbits at a larger radius than the other 2. Calculate the speed of Swarm A. So, what do we know about the speed of Swarm A? Well, that its radius is equal to 462 kilometres. Let's convert that into metres straight away. And that is a radius, it's not an altitude. That's a little trick sometimes with these questions you always look for. And what else do we know? Well, we know the velocity is given by this formula here, which is on our formula sheets. And we know that G, we know the mass of the Earth, that's on our formula sheet as well. And we've just been told R. So we substitute that into the equation. 6.67 times 10 to the minus 11 times, what do we say? 5.97 times 10 to the 24 divided by 462,000. Then we plug that into our calculator. And that gives us, well, my calculator says 29,358 meters per second, but we know, let's think about our significant figures, 3 significant figures in all those. So that is equal to either 29,400, or we could go 2.94 times 10 to the 4 meters per second. Okay, swarm B completes 15.1 orbits in one day, and the one day is 86,400 seconds, so you don't need to work that out. Determine the radius of the orbit of swarm B. So, couple of ways that we could go here, I suspect, just going through in my head. We'll do that working out over here. Can I use can I use this t squared equals 4 pi squared r cubed on gm formula? And I know, well, I'm going to be able to work out in this one here the period, and I know g and I know m, and I know 4 and pi. So that would seem to be the formula that I can use. So I've got to rearrange that formula. So r cubed will be equal to basically the gm is going to have to go to the top, divided by 4 pi squared. And then I'll obviously need to take the cube root to get that, to get rid of the r cubed. So to do that, then I need to work out the period. And so we know that it does 15.1 orbits in a day, so the period is going to be equal to 86,400. That's how many seconds in a day, divided by 15.1, which equals 5,721.85. I won't worry about rounding off yet. That's not my final answer. Seconds. So basically I need to put this number here into this formula here, and we should be at the answer. So let's go. Radius is equal to the cube root of 6.67 times 10 to the minus 11 times by 5.97 times 10 to the 24 times 571.85. That's still in my calculator, so I'm just going to use that number there. And that's got to be squared divided by 4 pi squared. And when I plug all that in, I should get an answer. So we get, what do we got? 6.91 times 10 to the 6 meters, which, let's convert that into kilometers, is basically 6.91 times 10 to the 3 kilometers, which 6.38 times 10 to the 3 kilometers is the radius of the Earth. So it's bigger than the radius of the Earth, but it's not that much bigger than the radius of the Earth. but it's more than 462 kilometres from a quick calculation in my head. So yeah, what I'm doing there is I'm just checking the reasonableness of my answer, and that seems a reasonable answer. I'll admit, the first time I did that calculation, I did get an answer that was greater than the radius of a geostationary satellite, and I went, that's probably not right. So I went back and redid the calculation. Hopefully I have got it right this time. Okay, it seems reasonable though. Suggest one reason why polar orbit satellites were selected for swarm satellites. They are closer to the surface of Earth, therefore make better measurements. What's a scientific way to say better measures? It's not quite resolution with magnetic fields, but they're able to make, let's just say, higher quality observations. It's only 1 mark. I'm sure that would get us the 1 mark. And finally, explain why the centre of these circular orbits must coincide with the centre of the Earth. Well, the force causing centripetal acceleration and that's what causes circular motion, and therefore circular motion is gravity. And we know that gravity, so that was our first mark. This is hopefully our second mark. Gravity acts along line joining centres. That's hopefully our second mark. Therefore, the orbit, or let's even say better than that, therefore the centre of the orbit, or orbits, must coincide with centre of Earth. Okay, hopefully that's worth 3 marks. So, sorry, that's going to be a long video, but I did want to keep that stuff all together. So if you do need to, if you have had to break it up into a couple of bits, that's okay. It's a bit late for me to tell you this now. Okay. If you like this video, then you're mad, but click like. And if you want to see more of this video, but maybe hopefully not so long and maybe a bit clearer, we'll try and improve, click subscribe. Cheers.